Again, we're continuing our discussion on maximum likelihood estimation. Um, we've understood what likelihood functions are, and we've also implemented a few examples of maximum likelihood estimation. And what we're going to do in this lecture is, in this video, is we're going to go over concepts of regression, particularly linear regression. And the reason we are going through this right now is because as we go on studying different optimization methods, we're going to keep coming back to a few regression examples that are going to help us understand implementations and the use of optimization methods in each of these problems. Okay. Now, I will say that I am introducing linear regression or regression in a very not very concrete way, because what I'm talking about is only going to be regarding estimation. There are a plethora of other concepts in regression that are studied. Regression itself can be studied over a span of various courses for various semesters. And so I'm definitely not going to be doing justice to the concepts on regression in this video. But hopefully you will walk away with some understanding of the elementary concepts of linear regression. Okay, so here's the situation that we might find ourselves in, is that what we have are variables y1 up to yn, which are observations or basically variables that are going to be called response. And I'm going to typically call the response variables, random variables, as y's, capital Y's. And I have x's that I observed and xi corresponding to each yi, which is going to be a vector that I observed, xi1, xi2, going up till xip, that is a p-dimensional vector. Okay, so this is the ith corresponding vector of covariates for the ith observation. So what I have basically by the end of this is I'm going to have xi, this vector, okay, this column vector, and yi. These I going from 1 to n are going to be my data. So each xi has a corresponding yi associated with it. Okay. Now let beta be a p-dimensional vector in R, so in Rp, and this is called the regression coefficient, and this is going to be one of our main parameters of interest in addition to sigma square, although we are actually going to be interested in beta quite more. Okay, and the idea is that given these coefficients, given these covariates or this information xi, I want to model a relationship between the response and my xi's in a linear fashion in the following way, that yi is going to be equal to xi transpose beta plus epsilon I, where epsilon i's are, so I should have written this, are IID normal 0 comma sigma square. So the idea now is that if I take my x, so let's say my p is, let's say, just equal to 1, okay? That means I only have, one xi over here, right? I don't have the rest of the vectors, I only have one observation. And I plot that xi, so x is on my x-axis and y is on my y-axis. And for each tuple that I have over here, xi, yi, I draw a dot, right? So this is an xi value and this is a yi value. Similarly, I have other data that I might have collected. Maybe, I have 100 data points, something like that. Okay. And so the idea in this particular model that I'm assuming over here is that for each xi, for each value of xi, what I have for this value of xi is I have a distribution of the corresponding value of yi. Okay, so let me rewrite this whole statement in the following way, that yi actually follows normal xi transpose beta comma sigma square, all independent of each other. And xi's, these xi's are not random, right? They're fixed. The xi's are fixed. So let me also write that information. So xi's are not random, at least for the moment. They can be random, and there are different ways of thinking about it. But for now, we're dealing with them as fixed. Okay. So now, if I look at this sort of modified way of writing the above particular model, then I know that for each xi observation over here, I basically have a corresponding distribution of y's. This is normal xi transpose beta sigma squared. Okay, which means that if I have a given value of xi, my yi's for this value of xi, is expected to take these observations, but I can also get these observations and I can also get these observations. And truly, that's exactly what I see is I actually, in my data that I saw, I got, I got an observation here, I got observation here, and so on. And I do this for every value of xi. So for all of the values of xi, I have, another, for the value of xi here, I have a similar. Now, they can have a different mean, right? So I don't have to draw the same curve here so that they have both the same mean. No. Notice that the mean over here is different for each xi. It's xi transpose beta. So over here, the mean can now look something like this. So the distribution can look something like this. They're going to have the same variance. According to our assumption, they have the same variance, but they have different means. Okay. Now, but the means are somehow related to each other, right? So this xi's, so the means over here are basically, beta naught not beta 1 xi1 plus beta 2 xi2 up until beta p xip, right? This is what these two things, this corresponds to, right? Xi transpose beta is an element-wise product in sum of those two corresponding terms, right? Okay, so the y's are basically linearly dependent on these x's via a parameter. Beta is what I'm thinking, and beta is what I want to find, right? So given a new vector of x's, if I have a value of beta, then I can go here and say, okay, well, you know what? This is the x that was observed, xi, and because I know the value of beta, I can sort of understand, okay, that this is probably my distribution. This is the meaning of this particular model over here. And then what I want to do is I want to find the beta that corresponds to this, data and to fitting this best model. Now, in this one-dimensional situation, my model is actually just yi equals beta 1 xi plus epsilon. Epsilon meaning that there are random errors. If there is no epsilon, then my data is just going to be the line, right? It's just going to be points on the line because if there is no epsilon, y is equal to beta 1 times xi, and given a value of xi, yi, the observed or random data, is exactly beta 1 times xi, so it has to be on the line. But that is not going to be the realistic situation of data, right? Which means that I want to add an actual error term that says, okay, sometimes I'm going to get values above it, sometimes I'm going to get values below it, And so in this way, I want to basically find the best possible value of this beta 1, which in this case, this beta 1, whoops, there we go, corresponds to the slope of a line. But also currently I'm thinking of zero intercept. Okay. I can also, and so that might be, so zero intercept means something like this. This might be a good line fit. Okay, so this would give me one guess of beta 1. I can also instead fit the following. Sorry, I'm running out of space here, but I can also fit the following model, which is going to be, let's try here, yi to be equal to beta 0 plus beta 1 x1 plus epsilon, where beta 0 now is an intercept term. And so that means the intercept need not be 0. And that line of best fit could be here. So this line would be my guess for beta 0 and beta 1. Okay, getting ahead of myself here, because really the goal over here is that I have observed my data, and what I want to know is, given information on the x's, on the x variable, can I understand what the y is going to be, right? So how are x and y related to each other is what I want to understand. But x's can be many x's, so I want to understand how can I understand y from these various given x variable information. We'll see an example towards the end. So I use capital Y to denote the population random variable, and we will use the small y to denote realized observation. So this is going to be the random variable, and these are going to be actual observed data. And another thing that I skipped over is if I take this model, if I take this model and if I accumulate all the yi's that I have and all the xi's that I have, I can actually write this independent sort of observation-wise model as a full model where y is the vector of responses, x is a matrix such that each row is xi transpose, right? And beta is still the same coefficient vector which is called the regression coefficient. And this y follows normal distribution, multivariate normal of size n, because that's the number of observations. Mean being x times beta and variance being sigma squared in, right? We've already discussed what a multivariate normal is earlier in a few lectures, right? Okay. Now, the linear regression model, like I said, is a model that is built to estimate beta, which measures the linear effect of x on y. I have some information on the x's. I want to know what y is. So let's take an example. Let's say that we are trying to understand the price of houses, okay? How much a house costs. And let's say I'm looking at Delhi, okay? New Delhi is where I want to buy a house. And I have information on various features or characteristics of houses. I've collected data on all the houses and noted its cost and other properties. So how many bedrooms are in the house? What is the square footage of the house? Is the house in a commercial district or a residential district? How close is it to the airport? Is it in a society or is it an independent home? And similarly, what kind of locality maybe it is in. Similarly, I have collected lots of information. All of these informations are my x, right? It's my independent variables that tell me some information about the house. And then the thing that I want to understand or guess or be able to predict is the cost of the house. So that is my y. Okay, so then I can build what is called a regression model to understand how does the price, how is the price, this Y observation of a house impacted by all of its other properties like square footage, number of bedrooms, whether it's in a society or not, etc. So how is the cost affected by all of these characteristics? That is really what linear regression tries to do. Okay. Now, again, like I said, there's multiple courses that can be constructed on regression. But here, what we'll focus on is only the mathematical properties that are going to be required in for optimization. Okay. Particularly, once I've written this expression down, I know that y's follow this distribution. So if I want to estimate beta, I can actually write down the likelihood function of beta from this distribution. Okay, and either from this or from this, I can write down the likelihood function. And that means I can do maximum likelihood estimation for linear regression. Okay, and that's really what we're going to do. So our focus is on maximum likelihood estimation, and that's really what we're going to keep focusing on. Okay. So in order to estimate beta, I can construct that, I can use the likelihood function to understand what values beta might take. So an estimation of beta. Right? So we know that y, so let me write it again, y follows a multivariate normal with mean vector x beta and variance sigma square in. In is the identity matrix of size n by n. So now my my likelihood is a function of beta and also sigma squared. Sigma squared is unknown here as much as beta is unknown. So we'd want to estimate both of those things. And so that gives me a product over all of the f of yi given x comma beta sigma squared. Now, I don't actually need to write this as a product form here. What I can do is just write this as f of my y vector given x and beta and sigma squared, because I know that my y over here, my y over here is distributed nothing is exactly like this, and I know from previous lectures what is the density of a multivariate normal distribution. Right? So I use that information to just write down its density. I don't have to worry about a complicated covariance matrix because it's just identity here with a sigma squared right next to it. So I get 1 over square root 2 pi sigma squared to the power n, e to the power minus half y minus x beta transpose y minus x beta divided by sigma squared. Simple. Okay. Now, this again, though, looks like a complicated expression, even though finding it out was simple. And we'd want to differentiate and do all of that to understand our maximum likelihood estimators. And so what I do first is I just take log. Right? So once I take log, I get log of my likelihood, which is, minus 1 by 2 log 2 pi. I think this should be minus n by 2 log 2 pi. Doesn't matter because it's just a constant, won't really come in the optimization. And then minus n by 2 log sigma squared, so that comes here. And then the exponent goes away, so I just get minus a half y minus x beta transpose y minus x beta by sigma squared. Now, what I want to do is now this thing is actually, this object over here is p plus 1 dimensional. Right? So it's not an easy quantity to look at because it's in higher dimensions. And in these p plus 1 dimensions, I want to take a derivative and set it to 0. Okay. Now, it's going to be a little challenging getting used to these ideas, but we'll try and go a little. So in this example, we'll go a little quickly. But when we get to the numerical optimization problems, we'll go a little slowly with the derivatives. Okay. So first thing I do is I'm gonna try and solve this to something that's slightly nicer as a function of beta. So y minus x beta transpose y minus x beta. First thing I do is I bring the transpose inside. So this just becomes y transpose minus beta transpose x transpose times y minus x beta. Now that I've done that, I can just pairwise multiply. So I get y transpose y, right? Minus y transpose x beta, so that's my first two terms here. Then I get minus beta transpose x transpose y plus beta transpose x beta. Now, what we note is that this term and this term are both transposes of each other, right? So they are both transpose of each other, but also scalar. Scalar meaning that they're not vectors in the sense that they're only one-dimensional. So if they're transpose of each other and one-dimensional, that means they're exactly the same. Right? So they're the same number, same quantity, so I can combine them. So I choose to combine this with this. So I get y transpose y minus 2 beta transpose x transpose y plus beta transpose x beta. Okay. Now at this point, I take this expression and I'm going to put it here in order to now take derivatives with respect to beta, right? So hopefully you're familiar with some multivariate calculus. Okay. So once I do that, okay, this term is equal to 0, doesn't have any beta in it. This term doesn't have any beta in it. So I just need to take a derivative of this term and just make sure I divide by 2 sigma squared. So I just put the minus 2 sigma squared outside and now start to take derivatives here. Now this first term doesn't depend on beta, so that's 0. Now this term has a beta over here. It starts with beta transpose. So this part just goes away and I just get 2x transpose y. Okay. This one also has beta transpose beta, so this is like a beta squared term, right? So because it's like a beta squared term, I'll get 2 beta left over, and that's exactly what I have. I have 2, but then x transpose x beta. So I have a 2 beta term left over because of that. Okay, and then now I just bring the negative inside, which means that this becomes the 2 and the 2 get cancelled with this, so there should be no 2 here. So this just becomes x transpose y minus x transpose x beta by sigma squared. Okay, and I'm just going to set that to 0 to get my actual maximum likelihood estimate. And just to jump here, when I set that to 0, this part over here goes to 0, and I just get that x transpose y minus x transpose x beta hat MLE has to equal to 0, which implies beta hat MLE is the very popular expression x transpose x inverse x transpose y. Okay, so this is what we get beta hat MLE to be. And now taking derivatives with respect to sigma square is fairly straightforward because it's just a scalar quantity. So over here, this part again is 0. This is minus n by 2, then 1 by sigma squared. And this thing is just a constant as a function of sigma square. So I just get the negative with the derivative of this thing becomes a positive, and I get by 2 sigma to the power 4. And when I set that to 0, I get sigma hat squared MLE is y minus x beta hat MLE transpose y minus x beta hat MLE by n. Which, if I take a quick look at this, this is basically, this transpose can simplify to 1 over n, I going from 1 to n, individual yi's minus xi transpose beta hat MLE. Okay, squared. This is what this transpose comes out to be. Now, what's really interesting about this is if we just take a second to understand what this is saying is, well, take your observed yi's, right, and subtract your estimated yi's from here. Because what happens is that once you have this model yi equals xi transpose beta plus epsilon, this is the population model, and you use this to get your estimate beta hat MLE. Right? You use it to get your beta hat MLE. Now you go, okay, what do I do with this? And what you do is for any xi, you're going to get, you can find out xi transpose beta hat MLE, right? So you take your beta hat MLE and you plug it in here. But you plug it because you never know what the errors are. So the errors go away, right? You can't say anything about the errors. And so essentially your y hat I, hat implying an estimate, is xi transpose beta hat MLE, right? So these hats, this is estimated response, right? This is what my model thinks that the response should be, and I can compare it to what the actual response was, right? And then take a square of that, right? And that is basically the error that I've made, right? This is the error that I've made in my fit, in my model, and that's the average of the squared errors is basically my variance on the errors, right? And now the one thing again I skipped over is that beta hat MLE is x transpose x inverse x transpose y. This assumes that x transpose x inverse exists. Okay, and if it doesn't exist, then we might have to figure something else out. Okay. Now I have not, and I mentioned this at a different time, that it is imperative to actually verify whether your second derivatives are negative definite or not. And so that's something I'm going to allow you to do on your own. But let's actually look at an example. So this is a popular example of the cars data in R. It's present default in R. I'm going to show you a plot where it has information on cars and the distance it traveled after the brake was hit. Okay, so the distance it travels after the brake was hit, this is your response. And the other measurement that was taken on the car was what speed was the car going at. Okay, so my actual response is the distance a car traveled after the brake was hit, and the information I have on the car is the speed that the car was traveling. Now, what I'm going to do is fit the model. Okay, the model that I'm going to fit is yi equals beta 0 plus beta 1 x1 plus epsilon I, sorry. Epsilon for the ith observation. There should be an epsilon I here as well. And this means that this is the intercept and this is the slope, right? And I noticed that actually in this model, there's a dot 1 next to it, right? This means I can write this yi equals beta naught 1 plus beta 1 x1. But this is x1i. Then my xi or x tilde I is essentially the vector 1 and x1i transpose, right? I have a 1 as well over here that I'm implicitly putting in for an intercept. So which means that whenever I have an intercept in the model, then the first column of that model, of that matrix X should be a vector of ones, a column of ones, right? So X over here is going to be two-dimensional, where I have 1, 1, 1, 1, 1. And over here is going to be the speed observed for each of those observations. So this is why I take C bind means column bind, a column of ones, and the speeds itself. So that creates my X matrix. But if I just look at X, I just see, a column of ones and the speed. This was 4 kilometers per hour, 7 kilometers per hour, 7 kilometers, 8 kilometers, 9 kilometers per hour. Okay. And if I were to plot my data looks something like this. I have speed on the x-axis and y and distance on the y-axis, right? And what I want to know is what is the relationship between speed and distance, right? What kind of relationship does it have in terms of what is the best possible line that I can draw for this particular data? This is the question that I'm trying to ask. Is this line good, or is this line good, or is this line good? Is basically the question I'm asking. Okay, and the maximum likelihood estimator for this line is, I just take X transpose X inverse, so that's this part here, X transpose Y. So this is X transpose X inverse, X transpose Y, and that's my beta hat. And turns out my beta hat has first component minus 17.6, second 3.33. So this is my guess for the intercept, not the actual intercept in the population, but my guess for the intercept, and this is the slope. And I know that this is the intercept and this is the slope because the first column corresponded to the intercept and the second column corresponded to the slope. And I can also estimate sigma squared because sigma squared is transpose of y minus x beta hat. So y minus x beta transpose times y minus x beta divided by n. And that turns out to be 227. So that's the variance. And I can actually plot the line on this. So this turns out to be the actual plotted line of best fit. And any point on this line is the corresponding y hat equals xi transpose beta hat, MLE. Okay, so this line is exactly y hat I equals xi hat transpose beta hat, MLE, and this distance of this point from this line, square it. So squaring it means that I'm sort of making a box, right? This is the amount of variation that I am guessing is coming from this observation. So points far away have this distance are going to add a lot more variance than points close by are going to add a lot less variance, right? So this contributes to summation yi minus xi transpose beta hat squared by n. Right. Okay. So this actually estimates my actual variance. Okay. Let's see. Now, we assumed implicitly the fact that beta hat MLE turned out to be X transpose X inverse X transpose Y, and for this to actually happen, X transpose X the inverse of this actually has to exist. So when does it exist and when does it not exist? And what might we do when it does not exist is something we'll discuss in the next video.